Dear students, welcome back to the lecture series on solid state. In the previous class, we had a detailed discussion on close packing of spheres in 1, 2 and 3 dimensions. In this session, we will have a discussion on the types of voids or empty spaces in close packed structures. We will also have a detailed discussion on the packing of spheres in simple cubic, body centered and face centered arrangement. We have seen that the structural units in a crystalline lattice are so closely packed together in order to minimize the empty space in between them, and that leads to a state of maximum stability and minimum energy. However, even if such structural units, which we may call them as spheres, so even though such spheres are so closely packed, still there may be some empty space vacant in between them. As you can see here, the spheres are closely packed. The upper row are placed in the depressions of the first row, and this is considered as the most efficient packing, but still you can see there are some empty spaces in between these spheres. So, these empty spaces or interstitial spaces between the closely packed spheres are called voids, or they are also called holes. So, let us see what type of or what kind of voids or holes are created during close packing of spheres. So, consider a single layer of sphere arranged into the shape of a hexagon, as you can see here. If you consider this image, consider a sphere in the central which is surrounded by 6 spheres. So, you can see that there is a vacant space or hole between these spheres in the form of a triangle. So, this triangular gaps or holes in between is called a trigonal hole in this figure, and that trigonal hole is highlighted in green color. Okay. So, the hole formed between 3 spheres is called a trigonal hole because it resembles a triangle. Okay. So, if we consider these 3 spheres, the space in between or the void in between resembles a triangle, and such a hole is called a trigonal hole. Now, consider a sphere in the middle. Okay. So, 6 other spheres are surrounding, and suppose if we place another sphere on the depression of the first layer. Similarly, we place one here or here, then we can see that a hole will be created by 4 such spheres. Okay. So, if we consider these 3 spheres, there is a triangular hole, and if we place another sphere on this void, there are 4 spheres then, and still there will be some vacant space or empty space in between, as you can see here. So, this is one layer, and on the top you are placing another. So, there will be a triangular hole like this formed by 4 such spheres. Okay. So, the vacant space in between 4 touching spheres having a tetrahedral arrangement in a close packed structure is called a tetrahedral void. Okay. So, a tetrahedral void is formed by 4 spheres which are in close contact with each other. So, on the screen you can see the tetrahedral hole. The centers of the 4 spheres lie at the apices of a tetrahedron. Okay, so, one will be here, the center of the sphere lies at the apices of a tetrahedron, and that is why it is called a tetrahedral void. So, the vacant space in between such 4 spheres is called a tetrahedral void. Now, we have seen that if there are 3 spheres which are in close contact, and when 3 spheres are in close contact, there will be an empty space or void between them which is of triangular nature, which we may call a triangular void. Now, when we add another layer of 3 spheres above it, okay, we are going to add another layer of 3 spheres above these 3 spheres. So, here you can see that the triangular void, the apex of the triangular void are pointing downwards. Now, when we add another layer of 3 spheres, we are adding in such a way that the apex of the triangular void of the new layer of spheres are pointing in the upward direction, as you can see here. Okay. So, the first layer, the apex of the triangular void points downwards, and on the second layer the apex of the triangular void pointing upwards. So, here you can see that a double triangular void is formed surrounded by 6 spheres. Okay, so, 1, 2, 3 and another layer of 3 spheres. So, this is a double triangular void which is surrounded by 6 spheres, and such a void is called an octahedral void. So, an octahedral void is formed by 6 spheres which are in close contact with each other. So, the vacant space between the 6 spheres having an octahedral arrangement in a close packed structure is called an octahedral void. So, when we compare a tetrahedral and octahedral void, we can see that in a tetrahedral void that is surrounded by 4 spheres, whereas in an octahedral void it is surrounded by 6 spheres. So, an octahedral void is much bigger since it is surrounded by 6 spheres. Now, let us find out what will be the number of tetrahedral voids and octahedral voids in a close packed arrangement. The number of these 2 types of voids depend upon the number of close packed spheres. So, let the number of close packed spheres be n. Then the number of octahedral voids generated will be equal to n. So, we have seen that an octahedral void is formed by 6 spheres. Okay. So, around So, 3 spheres here, and again on the top of it we have another 3 spheres. So, an octahedral void. Around each octahedral void there will be 6 spheres. And around each sphere there will be 6 octahedral voids. In short, if there are n number of close packed spheres, then there will be n number of octahedral voids. Now, what will be the number of tetrahedral voids? The number of tetrahedral voids generated will be equal to 2n. So, if there are n number of close packed spheres, there will be 2n number of tetrahedral voids. In the formation of a tetrahedral void, we can see that each void is surrounded by 4 spheres. So, each sphere will be surrounded by 8 tetrahedral voids. So, the number of tetrahedral voids generated will be equal to twice the number of close packed spheres. So, that will be equal to 2n. And the number of tetrahedral voids, as you can see here, is double the number of octahedral voids in a close packed structure. Now, let us see the characteristics of tetrahedral voids. As we discussed earlier, the vacant space or void is surrounded by 4 atomic spheres, and hence the coordination number of the tetrahedral void is 4. And how a tetrahedral void is formed? It is formed when a triangular void made coplanar atoms is in contact with the 4th atom either above or below it. That is either above the first layer or below the first layer. The volume of the void is much smaller than that of the spherical particles. And from geometrical considerations, we can find that if r is the radius of the constituent spherical particle, then the radius of the tetrahedral void will be 0.225 r, where r is the radius of the constituent particle. If the number of close packed spheres is n, we have seen that the number of tetrahedral voids is 2n. Now, next we will move on to the characteristics of octahedral voids. The vacant space or void is surrounded by 6 atomic spheres in an octahedral void, and hence the coordination number of the octahedral void is 6. And how such an octahedral void is formed? It is formed when 2 sets of equilateral triangles pointing in the opposite direction with the 6 spheres. In octahedral void also, the volume of the void is very small, and again from geometrical considerations, if r is the radius of the constituent spherical particle, then the radius of the octahedral void is 0.414 r. And if the number of close packed spheres is n, we have seen that the number of octahedral voids is also equal to n. So, these are the characteristics of tetrahedral and octahedral voids. Now, let us see how spheres are closely packed in simple cubic, body centered and face centered arrangement. First is the packing of spheres in a simple cubic arrangement. We know that in a simple cubic lattice, the atoms are present at the corners. So, there will be 8 such corners in a simple cubic cell, cubic unit cell. So, 8 atoms will be present. The particles touch each other along the edge, as you can see here. So, this is the edge of the unit cell. So, you can see that the particles occupying the corners and the particles are touching the edge. So, along each edge of the cube, two spheres are in direct contact with each other. As you can see here, this is one sphere and this is the second one. So, along each edge, two spheres are in direct contact or close contact with each other, and that is the arrangement in a simple cubic lattice. Now, let us see the coordination number. So, if we consider a lattice plane or multi-layered, consider an atom at the center. So, the atom at the center marked in red will be in close contact with 4 atoms in its plane, okay, 4 atoms in its own plane or its own layer, and one atom directly above the layer and another atom directly below the layer. So, in a simple cubic lattice arrangement, an atom in the center will be in close contact with 4 atoms, will be its nearest neighbors in its own layer, and one atom will be above the layer and one atom will be below the layer. So, total 6 surroundings. So, the coordination number will be equal to 6. And we know that in a simple cubic lattice, the cubic lattice contains one atom per unit cell. There are atoms only at the corners and each atom contribute 1/8 towards the total. There are 8 corners, so 1/8 into 8 equal to 1. So, it contains one atom per unit cell. Now, let us calculate the edge length. If r is the radius of one sphere, then the diameter of a sphere will be 2r. If we consider a sphere, so this will be the radius r. So, what will be the diameter? Diameter will be equal to 2r. Now, you can see here in a simple cubic lattice, two spheres are touching along the edge. Okay. So, from this centrosphere to this point it is r. Again from this the centrosphere to this point it is again r. Now, what is the edge length? Edge length is a. Okay. So, a will be equal to here r plus r. So, that will be equal to 2r. Okay. So, since two spheres are touching along the edge, the length of the edge A must be equal to the diameter of one sphere, and that is why it is given A equal to 2r. Again, the spheres are so closely packed here. However, the packing efficiency in a simple cubic lattice corresponds to only 52.4%, and this is lower when compared to 74% of packing efficiency in a hexagonal or cubic close packing. We will discuss in detail about packing efficiency and packing fraction in the later classes. Okay. So, for the time being, let us understand that the packing efficiency or the percentage of space occupied by these spheres is equal to 52.4%, and the edge length is given by A equal to 2r. So, next we will see the packing of spheres in a body centered cubic arrangement. Given here is a body centered cubic lattice. We know that in a body centered cubic lattice, the atoms are present at the corners and also at the center of the body. So, in a BCC unit cell, the atoms in the corners do not touch each other or contact each other, but it will contact the atom in the center. Okay. So, any atom in this BCC structure touches 4 atoms in the layer above it and 4 atoms in the layer below it, and hence the coordination number in a BCC unit cell is equal to 8. Okay. So, in a BCC lattice, the atoms are present at the corners and at the center. However, the atoms situated at the corners do not touch each other, but they can touch the atom in the center. Now, what about the coordination number? If we consider a multi-layered lattice, any atom in the center will be in close proximity or in close contact with 4 atoms above the layer and 4 atoms below the layer. So, in total the coordination number will be 8. And the number of atoms per unit cell we have discussed in the earlier classes. Atoms at the corners contribute 1 by 8 into 8 equal to 1 plus 1 atom at the center of the body. So, that will contribute to 2 atoms per unit cell. Now, calculating the edge length in a BCC type arrangement, the 3 spheres along the body diagonal touch each other, and the body diagonal is equal to 4r, where r is the radius of one sphere. So, the body diagonal is equal to 4r because of the presence of 3 spheres touching each other. Now, as per the geometry of a cubic unit cell having an edge A, if A is the edge of the unit cell, cubic unit cell, then the body diagonal is equal to root 3A. Okay. So, that is 4R is equal to root 3A. So, from this you can calculate the edge length. So, that is A is equal to 4R by root 3. So, that is given here, A equals 4R by root 3. So, you can calculate the edge length according to this equation, where R is the radius of one sphere. And in BCC type arrangement, the packing efficiency is somewhat higher than that in a simple cubic one, and that corresponds to 68%. So, next is the packing of spheres in a face centered cubic arrangement. In the previous class, we discussed 2 types of close packing of spheres in 3 dimensions, namely hexagonal close packing and cubic close packing. So, in cubic close packing, we discussed that is identical to a face centered cubic arrangement. In a face centered lattice, you can see that the atoms are present at the corners and also at the centers of each face. So, atoms in an FCC arrangement can pack more efficiently or more closely together, with atoms occupying 74% of the volume. And as we discussed in the previous class, this structure is also called cubic close packing or cubic closest packing, denoted as CCP. So, in cubic close packing, there are 3 repeating layers of hexagonally arranged atoms, as you can see in the figure. One layer is denoted as A, the second layer will be denoted as B, and the third layer denoted as C. So, this pattern will get repeated. So, we can call them ABC type stacking or pattern. And each atom contacts 6 atoms in its own layer, 3 in the layer above and 3 in the layer below. So, in this arrangement, each atom touches 12 near neighbors, and therefore, the coordination number in a cubic close packing or face centered packing is equal to 12. Now, let us calculate the edge length in a face centered cubic arrangement. And here also, when we consider the face centered lattice, you can see that the 3 spheres along the face diagonal touch each other. So, since 3 spheres touch along the face diagonal, what will be the length of the face diagonal? That will be equal to 4r. And as per the geometry of a cubic unit cell having an edge A, the face diagonal will be equal to root 2a. Okay. So, we have 4r is equal to root 2a. So, from this we can calculate a is equal to 4r by root 2. So, if we multiply and divide by root 2, then we get into root 2 by root 2. So, what is root 2 into root 2? It is 2. So, this will be 4 root 2 r by 2. So, 4 2 times. So, that will be equal to, that is a equals 2 root 2 r. So, that is given here. The edge length in a face centered arrangement or a cubic close packing, the edge length will be a equals 2 root 2 r. The packing efficiency we have already discussed, that is the highest packing efficiency will be present in a cubic close packing or a face centered arrangement, and that contributes to about 74%. So, we have discussed about the close packing of spheres in a simple cubic with a packing efficiency of 54%, in a body centered with a packing efficiency of 68%, and in face centered or a cubic close packing with the most packing efficiency or highest packing efficiency of 74%. And we have also calculated the edge length in these three types of arrangement. Now, let us discuss a few questions based on the calculation of the edge length or calculation of the radius. The first question, silver crystallizes in face centered cubic unit cell. Each side of this unit cell has a length of 400 picometers. Calculate the radius of the silver atom. So, you have to calculate the radius of the silver atom, and given that silver crystallizes in FCC lattice. So, for an FCC unit cell, the edge length, the formula of the edge length is A equals 2 root 2 r. So, you have to calculate the radius of the silver atom. So, if A equals 2 root 2 r, then r will be equal to A by 2 root 2. We have given the unit cell length, that is A is equal to 400 picometers. So, r will be equal to 400 divided by 2 root 2, and that will be given the value of r is equal to 141.4 picometers. Second question, tungsten crystallizes in body centered cubic unit cell. If the edge of the unit cell is 316.5 picometers, what is the radius of the tungsten atom? So, in the question it is given that tungsten crystallizes in the BCC unit cell. So, for a BCC unit cell, we have the edge length formula A equals 4r by root 3. Okay. So, we have to calculate the radius of the tungsten atom. So, if A equals 4r by root 3, so from this we can calculate the radius, r is equal to A into root 3 by 4. The edge length is given, A is equal to 316.5 picometers. So, we can find out r is equal to 316.5 into root 3 divided by 4. So, that will give you the value of R as 137 picometers. Question number 3. Silver crystallizes in face-centered cubic unit cell. If the radius of the silver atoms is 145 picometers, what is the length of each side of the unit cell? So, we have to find out the edge length, and it is given that silver crystallizes in the FCC lattice. So, for an FCC unit cell, we have found out the edge length A equal to 2 root 2 R. The radius is already given, R is equal to 145 picometers. Therefore, we can find out the edge length A is equal to 2 into root 2 into R, R is 145 picometers. So, that will give you the value of the edge length as 410 picometers. So, in a similar way, we can calculate either the edge length if radius is given, or you can calculate the radius of the atom if the edge length is given. Okay. So, in this class, we have discussed different types of voids or holes formed during close packing of spheres, the characteristics of such voids, namely the characteristics of tetrahedral and octahedral voids. Further, we also discussed about the close packing of spheres in different types of unit cells, that is in simple cubic, body centered and face centered cubic arrangements. In the next class, we will have a detailed discussion on the packing efficiency and packing fraction of various close packed arrangements. Thank you.